conference. Unfortunately, it seems that I cannot share my webcam for some reason. Also, I would like to welcome everyone who joined us yesterday in day one as well. It was a really successful event. We have a big number of attendees that stayed for, I would say, throughout the whole long 4 hours. Thank you very much for joining us yesterday, and as well, thank you again or back. Welcome back again to today's session, and also thanks to all and everyone who joined us as panelists yesterday. It was a really wonderful presentation that everyone have presented for us. Just going quickly before we start with the first session about our agenda for today, and also maybe review some of the agenda for yesterday for anyone who would like to attend or see the recording. So for today's agenda, I will be starting with doing sampled value testing. It will be presented by myself, Ali Hussein. And then our protection specialist, Andrea Bonetti, will be explaining or exploring the new concept of digital twins in a protection system. It's a very exciting session. I urge everyone to attend it. And last, we will have traveling wave and time domain based protection done by Muhammad Ashraf. Thank for him very much for attending with us today from SEL, Schweizer Engineering Laboratories. As for yesterday,
Ali,
yes,
excuse me. Are
yes.
you sharing the screen because we don't see anything?
Oh, sorry for that.
No, I got feedback also from some others that it's not only me.
I click the share button, but apparently, okay. Now,
Thank you.
okay. I believe everybody can see the screen now. So yeah, day two. We'll start first with sampled value, digital twins, and then traveling wave. As for yesterday's session, our presenters started with power swing testing, Mauro Borelli. It was a very interesting and very nice presentation. I urge everyone to go, and who didn't attend yesterday, to watch the recording of yesterday. And then a bus bar differential testing case done by Dr. Danish Babu from Indian team. Thank him very well for that. Also very entertaining. And then distance protection testing done by Mr. Or Engineer Muhammad Rashad from Alfanar Engineering Services. It was very informative. I thought I know distance protection testing, but really he opened my eye on a lot of very nice concept there. And last, I presented the line differential testing. So to give you more about our presenter for today's session, we have Andrea Bonetti for the second session. He is a senior specialist and product manager. He worked for Megger Sweden, our manufacturing site, for many years, and previously as well in ABB as a product management team, and as well contributed in writing many of IEC standards. So thank you very much, Andrea, for joining us today. And as well, protection application engineer Muhammad Ashraf from Schweizer Engineering Laboratory. He's having experience more than 13 years as a protection application engineer, an extra high voltage and high voltage environment. And as well as me, Ali Hussein, starting the first session. I am the sales and application engineer for Megger Middle East. For our session today, let me share my screen. But before doing that, please feel free to ask any questions. We have a panelist of expert with us today. Feel free to ask them any questions, and hopefully you will receive an answer live to this questions. So without further ado, let me share my other screen and go to the sampled value presentation. Okay, I hope everybody can see my screen again.
The screen is
Yes.
visible now.
Okay, right. So sampled value testing. For this session agenda, first I will give a quick introduction about sampled value in general. What do we mean by sampled value? How it's defined by different standards and what requirement we need to understand it. Then I will talk briefly about time synchronization, since it's a concept that it's pretty much go hand in hand with the sampled value. It's always required there. And then I will talk about sampled value testing. How do we conduct testing, or what is the testing concept when we talk about sampled values? And then I will demonstrate some of our solution and how we can help you in conducting sampled value testing. So without further ado, and of course, I would like to mention also, at the end, I have a practical demo video showcasing this solution for more clearance. So without further ado, let's start with sampled value. So traditionally, when we want to connect or attach our um, measurement equipment in substation, like your CTs and VTs, or instrumented transformers, we usually use, or we use copper wires for doing that, which requires a lot of wiring, a lot of uh, uh, cost for that. And in the end, most modern relays are numerical relays who convert this data to a digital data inside their algorithms. And based on this data, they operate for protection, control, etc. Requirement. Now, with the sampled value concept, it's moving this from transmitting this value in copper analog channels to a digital channel. That's why it's called digitalization for this. And the whole idea or concept is to move from this many connection to this just fiber optics or Ethernet cables. Nowadays, maybe in the future, they become something better for that. And to help us achieve this transition from the traditional analog connection that we'll be using for more than 100 years now to the digital world is some standards that we need to understand or follow to help us achieve this goal very efficiently and overcome many of the challenges that comes with this shift. So when we talk about sampled values, mainly the IEC 61850 standard that introduced them will be pop out, but IEC 61850 is very broad standard and keeps growing and growing and growing. So we have to go to the specific parts in that standard and also other standards that touch the subject of sampled value directly. So the first part of that standard is IEC 61850-9-2. It's what I would say defines the mapping of sampled value over Ethernet connection. So this part is mainly concerned with the Ethernet connection. Maybe in the future, when we have a better way of transmitting digital information other than Ethernet, the other parts may be added to the standard, but for now, -9-2. But this -9-2 is more of abstract standard that have a lot of things defined by the standard, but I would say become a little bit difficult to do. That's why a light edition, that it is not a standard by itself, but it's more of a guideline created by UCA, international user groups, to, I would say, minimize the moving part that the abstract standard left open for the user or the one who applying the standard to use. So it makes things easier, the light edition, and we will be talking mainly about it in this presentation. But two other standards that is very important as well, an IEC 61850 or sampled value, is the IEC 61850-61850-9-3, which is used for the time synchronization for defining a utility profile for a time synchronization method called BTB. We would discuss this as well in details. And it is based on IEEE, another standard, IEEE 1588. And last but not least, the IEC 61869-2. It is not part of the IEC 61850, but rather works hand in hand with it, especially for the merging units that we use for sampled value and the digital interface for these merging units. It is explained in this standard. So if we want to go more in detail in -9-2, it is, as I mentioned earlier, a sampled value mapped over Ethernet. But this value, once we connect it to Ethernet switch, it will be mainly, would say, published or multicast. But because of time delays and different network paths for different merging units, we will require synchronization or time synchronization. This sampled values, from the name sampled, you have to define how many samples happen per period or per cycle. So the subscriber to these published messages over Ethernet understand and able to analyze the value correctly, similar to what happened in the analog environment. The light edition, as I mentioned earlier, was introduced to help simplify things, because the abstract standard that was defined first, it was leaving too many open things and a lot of moving parts, so people kind of felt very difficult to agree. And one of the main objectives of IEC 61850 is to create interoperability between different vendor and also become future proof. So kind of left that one open for future proof things, but interoperability was mainly covered by the light edition. And as well in 2016, the 16869-9 improved on the requirement of the light edition as well by adding more profile to it. So if we mainly going to talk about these two standards, the 16869 and the 16-9-2 light edition, the difference between them basically is just in the sampling rates and some additional possibility to do time synchronization. For example, in the light edition, the sampling rate can be 4800 for 50 hertz or 60 hertz system, and 4000 for 50 hertz system, while in the 16 or 61869-9 prefers the 4800 for both 50 hertz and 60 hertz. And as well, the 61869-9 introduce different sampling frequencies for different application, like power quality metering and also DC control application, also introduced by that, and as well a new time synchronization method, which the light edition only added PPS, which stands for pulse per second synchronization method, while the 61869 added a new profile, which then become -9-3. So this talk about standard, can we simplify it? It's very simple. If we only take, for example, now just the light edition one, not the others, I will be having 80 samples per system frequency cycle. So 4,800 samples for 60 hertz and 4,000 samples for 50 hertz. Or a different profile also defined by the light edition is 256 samples. This is mainly used for what we called the power quality metering requirement, since you require sub-cycle knowledge to assess transient behaviors. Mainly each streams of these published sampled value messages will contain 8 analog signals. It will be 4 voltages and 4 currents. These 4 voltages and 4 currents could be like 3-phase voltage and neutral voltage, 3-phase current and neutral current, or could be used only, for example, 3 currents in 2 different merging units, for example, for differential protection. So these are the sampling values defined by the light edition. As I mentioned earlier, for the 50 hertz, we have the 4000 hertz packet frequency. And for the 60 hertz, it's 4800, because in both these protection requirement, we have 80 samples per cycle. So the cycle for 50 hertz is longer than the cycle of 60 hertz. And for power quality application, that frequency or sampling frequency become much more rating. As I mentioned, these messages will be published, so they are not specified to a certain device in your Ethernet network. It's not addressed to a specific subscriber, so anyone can really see them or subscribe to these published messages. And since these values are continuous, usually they will have a relatively high bandwidth consumption. If anyone familiar with the goose messages that is used or defined by the IEC 61850, they are not like the SV messages. They are published messages, but they are not like the SV streams, since the streams are continuous. And this network traffic management is very important when you are talking about sampled value. Your network should be able to withstand this stream and all the other traffic is available to it. Just to give you an example on this, if I have a sampling rate of 4800 for the 60 hertz per second, the bandwidth of that stream will be 5.6, approximately 5.6 megabit per second. If we connected as many as, for example, 80 stream to a network switch that have a length of 100 megabit per second, this will cause it to be jammed into the traffic and thus losing these messages which are required to be supplied or delivered continuously all the time from this stream. So that's why it is very important to have a network traffic management when you are talking about sampled values. And another topic that is also very important is time synchronization. When you don't have time synchronization between, for example, the different parts of your system, the merging units that is connecting to your IEDs, bad things could happen. And time synchronization is mainly needed to properly align the currents and voltages samples together for different protection functions, from measuring, from directionality, from comparing values, for example, differential protection. So if I have two different merging units supplying my IED, and these two different units, merging units, are running through different network paths, and the time delay for these paths are different. Without proper time synchronization, I will have misalignment, and the phase angles for these values, the currents and the voltages, will make no sense. And thus the IED or protection function will not operate correctly. The light addition defined or specify the pulse per second method, PPS, for time synchronization method. It's the method that we distribute the time over the different IEDs, and also defined a certain accuracy. But the IEC 650-9-3 new profile based on the BTB protocol defined maybe a little bit different accuracy requirement as well. And mention on that BTB, it's another method or another time synchronization method that really works very well with sampled value over Ethernet, because it's use Ethernet distributed way of distributing the time, rather than PPS, which is using just electrical signal, a pulse to each different IED. BTB is using the network switches to distribute the time. And it is first introduced, or the core standard for it is coming from IEEE 1588. But for sampled value usage now, the main specified one is defined by IEC 9-3. So time synchronization is very important and usually done by either BTB or PPS if you are using only the light edition. And thus it is important to as well test your system after connecting to it or implementing that. Now, for the testing, there are few concepts that is very important to understand. The first thing, when you talk about testing, conventional the conventional method that we use for conventional CTs and VTs is that we go to the substation, we isolate, and we connect our test switches or test plugs, or switch in test mode for the relay, and start doing the secondary injection to it. But this concept, when you are talking about sampled values and Ethernet switches, is not directly applied here. That's why the standard introduced a new concept of testing mode. And this concept is that you put your IED in a test mode. There are, I would say, 5 levels, and it is required like this for many reasons. This test mode is starting with the first mode being on or enabled, which is similar to what normal state, or I would say in service state for the IED. All the input will be processed, and then output will be generated based on the values. So it's like live state for your IED. And this is not something you can only do for the whole IED itself, but you can do it for each logical node. So each protection function, I can put it in test mode. I can put only the distance overcurrent, for example, or only the differential protection in my IED, or even only a certain small node of that whole function. So only distance zone 1, for example, I can put it in some relays to that level. I put a test mode for it. The second stage we have is blocked, means that the function is active, it is on, it is processing the input coming to it, but it's not outputting any contact or any outputs to, for example, breakers or switches, etc. Then we come to the test mode. The test mode is that the function or logical node, to be more clear on that, it is active and it is processing inputs, but only inputs that flagged as test, or I would say even in the new editions, maybe called simulation mode. It will only process these values that come with a simulation flag to it. So anything that is injected by test equipments will be processed in the test mode. And also the outputs of this process, if it's giving a trip or start contacts or operate conditions, it will be also flagged as test or simulated value. So whoever injecting and receiving the outputs from the IED will understand that these are the simulated values that he is being injected in test mode. Then we have a test/blocked mode. This was introduced mainly when people are using a combination of both digitalization messaging, like sampled value and goose, and the physical contact, for example, physical trip contact, physical operate or trip, or physical start or pickup contacts. The blocked condition will block these physical contact, but will still publish the goose messages since they are a hybrid system that use both in combination together. So this mode is very important. And the last mode is being off, means the a logical node or function is completely off. It's not processing or accepting any inputs or processing anything or generating any outputs. So it is very important to understand this test mode when you want to do testing. And to give even more clarification on this, when you are doing any testing with a test environment or a live substation, you put the 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 function in test mode, and any messages that you want to deliver to this function or IED, you put
Ali, can you hear me?
Apparently, there's something wrong. In
Hello, I believe I lost the internet
Yeah.
connectivity for a very short duration. I stopped the presentation. I noticed the message coming up showing loss of connectivity. So, was I in this slide when I lost the connection, or the previous one?
You were talking about this slide.
All right, good. So we are not far off from that. All right. So when you want to do testing for an IED with sampled values and even goes messages, you will set your test equipment to publish these sampled value and ghost messages and with a simulation flag to be true or 1. Now, if a device in normal service mode with simulation flag being false, it will not accept these simulated messages. It will not, even if it's subscribed to them, it will not process them at all. So once you put your device under test, or I would say just slice of it, the logical node with test mode or simulation flag, it will start processing these messages and outputting simulated flagged outputs as well. That's why test signals should always be injected with simulation flags, especially in very, I would say, or in a live environment. And thus, devices should only accept these under test mode as well. Since once you start connecting and start publishing, even if you are not injecting anything or putting any value, everybody in the network will see this. So you need to make sure that everything is not in, or anything other than the device you want to test is in test mode, and also maybe the hardwired outputs are blocked or using test/blocked mode from operating the process in case you are in a hybrid environment. So testing requirements, this is some few things that I would mention very quickly. You need a way to import SCL files. SCL files are substation configuration language files that have all the information about your substation, all the communication mappings, all the capabilities of your IEDs, all the description for them, and be able to do comparison for these SCL files and what you have in your network, and also able to copy, I would say, the information from these files to your test equipment for the specific device that you are planning to test. And also for the comparison, you need the ability to scan the network to see that what you have in your network is exactly what you have in your files to start doing the test. And it does help to have an easy setup or a good knowledge as well, and a good device that can help you in publishing sampled value and ghost messages, either by subscribing or even publishing these messages. But there are a few things that is very important to understand when you are dealing with testing in IEC 650 environment. You have to really be careful when you are doing that, because once you start publishing anything, everybody will be able to see this. So you need to be very well aware of who is subscribed to this and which test mode or in which mode this IEDs are in at the moment. You need to have, I would say, a real time visualization of your whole system, which many software tools now help you understand very quickly in real-time environment. You need to be very well aware of how IEC 6150 or messaging and communication is defined, and have a clear procedure in doing that as well. I would maybe recommend you to work with a dummy setup, just a small network, if that's possible for you, if you want to learn, and have trial and error and see how things like that. But also we can really help you in this manner. We have quite a good team for that. Andrea Bonetti, my colleague from Sweden Factory, have done many testing in this and are familiar with many of the difficulties or challenges that can really arise. So a quick shout to him, Andrea. If you would like to add any comment in this as well, please feel free to do that.
Yeah, yes. Thank you for mentioning me. I have worked with IC6150 for relay protection applications since the early 2004, where both in commissioning and technical support, troubleshooting, etc., and also training. As I said, 2004 is quite many years ago. And I'm not part of the IC6150 committee, but I'm part of the relay committees in IC that deal with IC6150 for protection applications. So 6150 is not the protection application committee. The protection application committee is called the TC95. And in TC95, we are dealing with a technical report that says how to make a relay, how to test a relay, how to specify the relay performances when 6150 is used. So it says how to use 6150 for relay protection applications. And I have put a link on that on the chat. So we wrote a paper, me and the other people in this group, describing the job. And I think the technical report will be ready hopefully next year. It's a very important technical report that will simplify the technical specification for all of you. I don't think we will have time to discuss this more unless we have some time in the end.
What I am saying here is that we are available to help you understand, because we understand that this shift from analog or conventional methods that we use for our substations, it's going to be quite a big effort, or I would say a big jump, since we'll be using that since like 100 years or even more than that. So we are here to help you in this jump from training, education, educating you about that, helping you and giving you guidelines on how to test in IEC 61850 environment for protection purposes as well. So for that, I would like to introduce our, I would say, new test equipment called SVGS, or maybe previously Smart 1588. It is similar to Freja 500, or I would say smart units, but the sampled value counterpart to it, or the IEC, full IEC 650 compliant unit to it. It is out there, officially released, but still in maybe early development or development stages to comprehend all the wide area requirement by the testing committee as well. So basically it have 5 RJ45 ports and can supply you up to 3 streams simultaneously, either 50 Hertz or 60 Hertz, the light emission profiles, the 80 sampled per cycle. It also can be synchronized using IEEE 1588 BTB and also the IEC 61850-9-3. And if you are not having that, you can also use PBS. There is an input for PBS. As well in the future, it will be able to, I would say, synchronize even the SMRT and the Frege units to also work in hand with it. This is maybe a requirement when you do merging unit testing rather than, I would say, functional testing directly to IEDs by sampled values. This is a quick maybe a slide of where this unit fits. It fits in mainly the digital world, but works hand in hand with the Frege 500 or SMRT units that we supply for secondary injection kits. So the smart or Frege 500 will inject before the merging units like normal conventional CT, while the SVSG or Smart 1588 will be injecting directly in the switch or your process bus network. And it will be also mainly controlled by similar software that we have before, the RTMS software, to use this new test equipment. But in addition to that, we have another software called SVA or SV Analyzer that will configure this test equipment. It's basically like mapping the addresses for the streams to the relays or IEDs to publish them based on our requirement from profiles, addresses, and so on and so forth. And also able to subscribe to streams that is being published by merging unit, actual merging unit in your environment. So if you are injecting real analog values in your secondary of your merging units, you can measure them using as a sampled values using SVA as well. I have a small practical demo video I would like to show you done for this small setup. Here we have an ABB REX relay connected to a small network defined by this switch. And I have the SVGS or Smart 1588 connected to this network that will publish sampled value to this IED, and we'll see how these values are being configured very briefly and how been published, been injected as a values, and been measured from the relay as well. So let me run that video very quickly. It's done by my colleague Mohit Sharma. Show you from the start. You will deal with this unit as similar to normal Frege or SMRT unit. Connect to it, establishing communication. You see the unit here. Connect to it. He will just define very quickly the frequency that we'll be using, since this is very important for the profile of the unit. Can you see, as you can see here, if I stop the video, I have 12 currents and 12 voltages, which assembled for 3 streams. Each one have 4 currents, 4 voltages. So in total, 12 current or 12 voltages, all coming out of the Smart 1588. And since this is just digital values, it's very easily to get this number of streams. Just define the frequency. I think also it's just the lead and phase angle, since in America they are used something differently. Then he will go to the SVA software, sample value analyzer software. You can see here you have the 3 streams that can be configured manually, or you can just import substation configuration language file, basically a file to configure these streams. So there are these blocks for the stream that you can just basically just copy to your configurator, and as simple as that. Just this is like the connection of your test plug. Of course, you have to take all the preparation and selecting the appropriate test mode and knowing your all system. This is just for demonstration purposes. Configuring the PTB clock and checking the status for it. It is working correctly. Allow you to configure the 5 ports that you have. So he is using port number, I believe, 3 to publish these sample values. For goose publishing or subscribing, or you can also use the same port or different port based on your configuration. And last but not least, configure the sampling rate. Since he's using 50 Hertz, he need to make sure that he is configured as 50 Hertz. And last, then he will download these values to the test kit. But first selecting the mapping. So stream 1 will be I1 to I4 and V1 to V4, and stream 2 will be other values. Now he will go back to RTMS software, which is used same as the normal software. Just adjusting the phase angles. Since I4 is not, I believe, configured in the relay, he just jump over it, and also V4 at the same time. Now he will first read these injected or published sample value from his network. So he can read the values for stream 1 and stream 2. Based on your CT ratio, sample value has shown 200 ampere, the correct phase angles. Also using Wireshark to verify these Ethernet packets. Wireshark is a software that can show your network traffic that you have connected to. It is very useful software when you are dealing with network traffic, and anyone really doing testing for IEC 650, I urge them to get some knowledge about the software and how to use it to analyze what you see in your network. And last but not least, he will log into the IED and check the measured value there. The same values that he's been injecting using the Smart 1588. Just checking the information about the accuracies and time synchronization that he have. I don't think we have much time really to continue on this demonstration. Thank you everyone for your time, and I hope this become more informative and enjoyable session for you all. Now we will start taking questions and also helping me in answering this question as an expert, Andrea, as well. Please feel free to drop your comment anytime for this question. I believe you already have answered some of them, maybe.
No, there are not many comments. I have. I felt I should give some links to some papers and articles that we have been written on this, because it looks much more complicated than what it is, and if
Yes.
you do it through in the correct way, it's not so complicated. But it's a standard that is not written only for relay protection testing, relay protection applications. So we have to do our own profiles to make sure that we know what we do. We have to speak the same language. Okay, let's see if we have some questions in the question.
I believe we have some questions here. I think it's only one question, and it's not a question, it's more of a statement. It's more complicated than conventional testing. Needs heaps of software, and you must need a good connection of internet. As Andrea have mentioned, yes, it is, I would say, more complicated if you compare it to the conventional way of testing. But if you know what you are doing, or have a good knowledge about
Okay.
how your substation is defined, or how everything is connected together, testing will be really easy. And I think with the help of softwares, it can be more even automated rather than doing it physically in the conventional way. So seems that we are out of questions. Our next session will be on digital twins, that will be presented by Andrea. We still have a few minutes before we start that session. Still, the floor is open for anyone asking any question. Please feel free to ask this question, and it will be our pleasure to answer these questions for you. Another thing I would like to know, that in the public chat, Andrea have added a lot of papers explaining testing and explaining the concepts behind digital inputs and digitalization or sampled values. whatever you want to call it. Please feel free to check these links and papers for that. Okay, Andrea, whenever you're ready, after 2 or 3 minutes, you can start with the next session.
Ali, I'm actually ready, but I cannot share, and I answered some questions, but they ended up as a instead of answer, they ended up as questions because I'm for some reasons. Okay, now I'm panelist.
Okay.
Yes.
Yep.
So,
now you have the right to present, please. Whenever you are ready.
So I will do like that. And I should be able to share. You please let me know if something doesn't work. But I hope you can hear me and you can also see the screen.
Yes, we can hear you, but we cannot see your screen yet.
No. Okay. You cannot see my screen and not even myself? Okay, screen 1.
Yep, now we can see. Yes.
Well, a lot of clicks, definitely. So I'm just trying to minimize the millions of windows that I get on my screen, but let's have a look. So you can see my screen now, or maybe you can see myself, I don't know.
We can see your screen, but unfortunately, WebEx system, I don't know, have an issue in
I see that.
showing the webcam for some reason today.
Okay.
I cannot even share my webcam as well.
Anyway, let me start. It's 10 o'clock. Thank you. Say thank you to all of you that are participating, and thank you for you guys that have organized this conference. It was a pleasure to be there yesterday, and it is a big pleasure to be here today. Also, I would like to say thank you to all the external partners, speakers that have spent the time to provide the slides and to participate here. So I'm going to talk about the digital twin, which is something definitely new. It happens very often to me that I hang up to the new things, and then hopefully there will come a product that can be used by the majority of you. But we have it. It is not a PowerPoint. It is a PowerPoint, but there is a facts behind the PowerPoint. So we have the situation under control and under development. I have to say, what is that? Before I enter into this detail, and for some reason my screen doesn't work. Yeah. I want to say thank you once more for yesterday. I hope you can see this second screen because the delay for me is huge. Can you see this animation and the LinkedIn post?
We can see, Andrea.
So
but,
we have to be patient. I know from my clicks to when it happens, it takes a few seconds. We will learn about that. We have got more than 2,000 views only for this simple post. It was only private for the network. So I think it was a successful, definitely. If you measure from the number of views, it was definitely a successful meeting. I hope we will get the same success today. Let's go to our digital twin. I have presented something. This is the first time I'm presenting serious serious in terms of time presentation of a digital twin. I have done some 10-20 minutes more, not more than that before. And some comments is, oh, now we are talking about digital twin. First, you have been talking about 61F50, and now we got another buzzword. So is it a buzzword, digital twin? Well, if it is a buzzword, we have done it really buzz, because Electrical Tester, which is our Megger magazine, the issue was released in August, so a few days ago, maybe a few weeks ago. We have a top article of the Electrical Tester is on digital twin. And I know that this guy that you see on the movie here is participating in this meeting. You cannot hear what he says, but I wrote what he says. Niklas Wetterstrand is telling what you see on the screen coming up. I'm not able to show you the audio, unfortunately. So Niklas Wetterstrand is our manager for relay protection in both Sweden and America, United States, and is introducing this article that I really hope you can read about that. This article goes in some details, and I will go in some other details in our presentation.
So, hi Andrea. So this ET magazine is available freely on the website. I can
Yes,
just share that in the
yes,
chat section.
Are we going to share the PDF of these slides? Because all the links are on my slides.
Yeah, I can just share that in the chat
Yeah, we
section.
can do that as well.
Okay, so
I've
that
just shared
everybody
it in
can
the
reach
chat
them
section.
easily. Yeah.
Yeah. So it is not password protected. It is just free.
No, absolutely not. If you have problems in reaching links, etc., drop me a message on LinkedIn is the easiest way to do. So again, what is this? Digital twin, I still haven't said any word about that. Is it a sort of simulation? And now I have Ali that luckily introduced this concept right now. You talk about simulation and you go back to IC 61A50, and then you think about digital technology, and 61A50 is a standardized digital technology. So let's have a look about what simulation means in IC 61A50, which is a standard, so we have to consider it. We are not doing something outside the standard. We have a sort of a simulation bit in our goose messages or in our sample values messages. You raise this bit, I make it simplified, and you tell to the network, this is not a real message, this is a testing, this is a message from a test equipment. It is intended to be used for some tests. This allows to discriminate real messages from simulated messages, and without that we need to disconnect some equipment from the network for testing. It looks strange, but it's a very good idea, and it works very well if used by everybody. And then we have the so-called simulation of the data model, which is related also. Data model is how you describe the protection functions, how you describe the control interlocking functions, the signals, start trip signals. This is the data model. And the data model, the signals are called the data attributes. There are some names that we love, but at the end, we have standardized how the way you call these signals. This is what we call data model. And this is described in a so-called SEL, system or substation system configuration language, which is 6150 language. And we can, when we have this SEL file, we can read the SEL file, which describes the relay, and we can change the status of some of these data attributes and then send it out as a goose message, a sample values, no, but we could send sample values as well, or send us a report control block, a report message in MMS report without any link to the reality. The relay doesn't trip at all. There is no power system fault, but I can simulate that the trip from the relay is generated and is sent as a ghost message. This is a simulation, which is a very important concept because we test a SCADA system with that, for example. So, as I said, here we have 2 relays, and here we have a test set, and we have one relay is sending a real goose A to the relay B, which is subscribing, that is receiving the goose message. And we have the Megger test set, the Omicron test set, the double test set, anybody test set. This is a standard word. Everybody has to behave in the same way. And the Megger test set sends a goose message that is with the simulation bit 1. Both messages are on the network, both, but the relay doesn't consider the Megger goose message until we tell the relay receive simulated messages. Very, very simple, but it has to be understood. As I said, it's very important for commissioning, especially for maintenance of 6150 protection systems. But we're not going to talk about that. For the data model, as I said, we can simulate from the SCL file, we can simulate devices. There are many tools that are able to do that. Usually, these tools are related to manufacturers that provide the SCADA systems because they require a certain SCADA competence to do that. And here I have a Siemens SICAM. There is a reason why I have a Siemens here in this presentation. You will understand that. So as I said, we can simulate the messages sent by the device without having the device. And yes, the PTRC is a P protection trip. So it's a signal for the trip. Could be general trip, or could be some trip dedicated to some distance protection function, etc. So we can raise it without having the physical relay there. So we have software tools and we have hardware tools where we can also simulate a goose message. We take the goose message from the SCL file, we put it on the network, and we decide that we raise a bit number 7 to the goose message. A bit number 7 means trip. But there is no relay there physically that is tripping. And these tests are very important for interoperability tests. You have 2 relays from 2 different manufacturers. And manufacturer A is available because you are manufacturer A. Manufacturer B is not available yet. It will come in the substation, but you are not in the substation. You want to simulate the manufacturer B sending the goose message that you will send without having it there. And you don't care if manufacturer B will really trip or will not trip. You want to simulate the goose messages because you want to verify your own configuration and settings. So there is a big benefit in this data model simulation. But I am a relay protection engineer and I have some issues here. I have my relay protection, I have my settings of my timers, I have my configuration. The relay can be blocked, it can be unblocked, it can be accelerated by a carrier send, carrier receive signals, whatever. So I want to see that, and this cannot be done. How fast is a PTRC op signal, so the trip signal raised? This depends, of course, on the relay setting and the relay algorithm, as I said to you. So the fact that out of that signal we generate a goose message, it's very important, but it's not the main purpose that I have when I am a relay protection engineer. I have to make sure that that signal comes within 20, 25 milliseconds from the fault inception, or after 4 seconds, if this is my timer. Exactly. What happens if the PDs for the distance protection function zone 2 timer is wrongly set? Instead of setting to 0.4 seconds, which normally we do, I set it to 0.4 milliseconds because I didn't read that the unit is in milliseconds. And this happens. You will not be able to see this with the data model simulation. It is again an application issue. And the setting is wrong. To see that the setting is wrong, you need to measure the time from when the power system fault happens to when the protection function operates or trips. And what happens if the protection function is blocked? I go in the data model and I raise a trip signal and I send a goose message on the trip signal. Perfect. Unfortunately, the trip function was blocked. The data model doesn't care. So I hope I'll give you some examples to more expert, less expert to understand that the data model is important for many things, but it's not the solution. It does not allow me to test the application in a simulated environment. And the list can be very, very long. So are there any solution to these questions? Unless we start to do the Rubik's Cube now in 10 minutes. I want to test the application. And then here we get the genius. Take the protection device, take a test device and run the test. Yeah, yes, okay. That is, we got a comment also right now on the 6150. No, now I did it with wires. Of course, we need a physical protection device, a physical testing device, a physical connection, a physical person there to drive them and run the tests. Why? Because the application is not standardized. The data model is standardized, but not the application. So how fast the protection function trips depends on the algorithm. Protection depends also on the relay settings, depends on the engineering and the configuration of the protection relay. The real application, the relay application, and how it works is a proprietary of the vendor, and it will remain proprietary of the vendor. It's not standardized. We have only standardized the data model. So we have a gap that we have to fill. And that is, I wish to have a virtual representation that serves as the real-time digital counterpart of the physical object. I would like to have a copy, digital copy of that relay. I would like to have a digital copy of that test set and put them together. This is actually a definition of a digital twin. So the digital twin is a digital copy of that physical device. And C-Protect 5 from Siemens has done since 2 years ago, and we have been contacted, and we developed something similar. I will say later. Virtual testing on C-Protect 5, they call it digital twin, and it's a digital copy available of a C-Protect 5 device. Megger, we recently did a digital twin for the relay test set. Now you see only a small one, SMRT1, but we have a digital twin for many other test sets. And it's a digital copy of what the relay test set will do. And now you have to see that it's not really buzzwords. I hope you understand that when we have a digital twin for the relay and a digital twin for the test set, and we are able to make them talking somehow together, we can do, no, it's not. I get a pop-up, no, it's nothing to do with Scout. And Scout is based on the 6150 data model. It's sort of ITT 600 from ABB or Simatic, the Siemens software I did show you here. It's a sort of SICAM protocol test system. They are good equipments for testing the data model. That's the only way I have to manage that. I saw the question as a woof, as a flash on my screen. So I'm not. I'm answering to that. Maybe if some other question will come out, I will try to answer at the same time. That was a nice tool. So many test sets don't really. Many tests don't require a physical relay to be done, but they must be done, and I will explain what I mean with that. When we have a possibility to perform a virtual relay testing, we can make that several people can work in parallel independently from each other, because there are 50,000 copies. You can have as many copies as you want of the same protection relay, and one for me, one from somebody else. And we can have 50,000 copies of the SMRT1 or whatever. easy to get remote support from experts and colleagues. Yeah, because you do the tests at home. You can prepare your tests at home and you or in the company, and you don't have to go on site. It's more comfortable environment, less time pressure on site because you have performed many tests already at home or in the company, so you know that it works, and you can do the job you want. For sometimes, for example, I did some of these tests during the weekends because you don't have to have the connections, you don't have to have 50 volt power supply, etc. So of course it's much more comfortable. Geographical barriers can be eliminated. Think that you can have two digital twins connected to, and now I'm talking for Siemens, so I apologize if I say something wrong, but I believe it is possible to have the two line differential protection relays connected to the digital twins, connected to the real multiplexers into a communication channel. I guess, I'm not promising that. And anyway, you can, I know you can connect these two relays together in the virtual world and test the line differential protection without doing the test we have talked last yesterday, the presentation of yesterday. This test can still be done in the substation, of course, but instead of performing hundreds of tests, you perform only 2 or 3, because the others you have already done in the virtual. So we can also invent more. We can create a test set that doesn't exist in the reality, that gives you many currents, and test the completely buzzer protection with 20 feeders in the virtual world. This test nobody would perform in the physical world, but it could be nice if you trust it. You trust for 1, 2, or 3 bays. You can trust also for 20 bays. So this was something we call a virtual super combination of super test set. A test set that doesn't exist in the reality, but actually is performing the signals, voltage, and currents. The major benefit of virtual relay testing is actually that validated, when I've done all my tests, the validated relay files, so Dixie in this case, can be reused in the substation against the physical relay. And the validated tested files that I have run in my digital twin, SMRT Freja, can be reused in the substation against the physical Freja. So at commissioning, you know that these two guys together should work because you have seen them working together into the and performing together into the simulation world or digital twin world. Less commissioning and less troubleshooting on site. You can test the relay without burning it. I mean, for example, for training, you can inject 30 ampere. We can inject 60 ampere, but not continuously. You can inject 30 ampere continuously for several hours from a digital twin test set into the 1 ampere digital twin relay without that it burns. When you are done this test in the digital world, you are already comfortable with this situation in the real world. So you have already the competence on how to handle a test set, the relay tool, Dixie, how to download, upload the settings, how to perform the test, you know, because you have used it. It's a sort of deja vu. You are not going into the substation with this feeling I'm starting from scratch. You go into the substation with the feeling I already know what should happen. If something is different, I may also know where to do the troubleshooting. Training. I had a discussion yesterday or this morning on LinkedIn about that, and I was not thinking about this, but training is a powerful application for digital twin testing because you can have as many relays as you want, you can have as many tests as you want. If anybody of you, and there is some people here that are doing training for profession, and I have done training many years, one of the problems is that you want to have groups. you need to have groups, 4 or 5 people sharing the computer, sharing the relay, sharing the test set. And the group is good, by the way, because the people can talk together. But it's also bad because many of the people would like to sit there alone and think about themselves, and they cannot do it because they have to interact with the group. So sometimes it's good to have your own computer and your own test set and your own relay. And now it can be done. And here there is a LinkedIn post for a guy that I don't physically know, but I virtually know from LinkedIn, that has done a training for CProtect 5 relay protections because they have the digital twins. At the end, as I said, the practice is still the practice. So I don't think you should do a digital twin training, but you should do a digital twin training for 80% of the time, and then divide people in groups where they share the computer and the relay and the test set to put in practice what they have done in digital world. So they had the possibility to think by themselves, and then they have the possibility to go into the group and share their opinion on what happens. I think it will be a very good experience to produce such a training. So regarding the commissioning site, the commissioning time at site, if you take a commissioning virtual test that you perform, you can take a subset of them. You say, okay, I've done 100 tests. I take the most important, the most 20 important ones, and these 20 important ones I will do on site just to verify, you see, just to verify that everything behaves like in the virtual world. And then if it's not, of course, you have to open the box. But if it behaves like it was behaving before, you have the confidence that your tests were okay, and that still the system has been mounted and connected and set and configured as it was supposed to be done. So you perform a subset of the testing on site. And also, of course, you will need to do some new tests on site because you have new connections that you didn't have before. So you have to take care of some situations that you never had before. And maybe you also have some new requirements for the customer. If you have done commissioning, you know perfectly what I mean. So some new tests shall be done on site. You cannot avoid this, of course, this is a reality, but not so many. Consider that all these tests today are performed at site. So the majority of the time will be saved. And especially not only the time, the confidence that you have into this test engineer at site, that he has already seen the system working. The digital twin for a Freya and a Freya, or in Sweden we say Freya, in English we should say Freja, and SMRT test sets, it's working like that. It's based on RTMS software, where you know that we had a sort of simulation. It's not digital twin, but that was the fact that triggered all of this project. The fact that we had something called simulate device triggered the interest, and we then developed the digital twin. So that, if you know what it is, it's not a digital twin. It's 50-50, let's say. You can connect to a real test set, or you connect to a Megger digital twin test set. And when you connect to this digital twin test set, you can choose at the moment SMRT1, SMRT410, Freja 546, and those ones you see. For the moment, we believe that these test sets are good enough. So what happens when you are selected to run RTMS software against a digital twin test set? Well, the RTMS software normally communicates to the real test set through Ethernet port, Ethernet traffic, cable at the end, or USB, but a cable, physical cable. Now there is a physical cable, but it's not there. It's in the computer because the test set is running into the computer. So the communication is there, but it runs into your computer. So you don't see it, but it's done. RTMS doesn't even understand that it's a digital twin. So the test engineer, me, you guys, can prepare the test in the same way it's done for the real situation. Yes, yes, no, not for this communication, no, but the digital twin relay can perform 6150 tasks, and we will be able to perform 6150 tasks. We are not ready yet. This is step number one of the digital twin world. We need also some users to give us a feedback and tell us in which direction to develop, because this can develop in millions of completely directions, and the difficulty of the technical manager is to decide which is the most important direction. So you prepare your test in the same way. I've done some example. I've done a trip in zone 1, no trip in reverse, because I don't have any zone in reverse, and I have done a switch on to fault trip, like you do normally in Fraser SMRT. And then you run them against the digital twin. What happens when I run them? You press the button, run. And I would like you to understand, this is, for example, a phase towards fault in forward direction. I say, what would happen? Where are the electrons? Where are these currents? Where are these ampere? Where are these volts? At the moment, the test is run via interface between the digital twin test set and the digital twin relay. So we have to listen to the digital twin relay. That's why we had to partner with Siemens. How do you want this data into your relay? And for the moment, the data is in COMTRADE. So next step will come soon, but for the moment, data is in COMTRADE. So the test runs, and all the samples are generated, all the values are generated like a normal test set, but then at the end, it says, okay, don't save COMTRADE because you did strange stuff, you did the wrong test. Save COMTRADE without viewing, or save COMTRADE with view with RTMS COMTRADE viewer, so you can have a preview of what we are going to save. This is our output. That is what happens. We create, you can have a preview with our previewer, or if you, and then you save it, or you just save it. And then that's all. But be careful, this is not as save as COMTRADE from RTMS. RTMS runs against a digital twin, which runs and gives also voltage and currents as it would do in the reality. And the output is, in this moment, in COMTRADE. If you want the output in another way, we will fix the output in another way. It depends on what interface the digital twin is going to ask us. The test files are saved in the same way as they are saved with the real test set. When the files can be reused, the files can be used with the real test set, same file. When you open the file, just make sure you connect, of course, not to the digital twin, but you connect to the real test set. So now, when we connect to the real test set, we are in the real world, reusing the files generated in the virtual world. The fact that we are using a COMTRADE to pass data between our digital twin and the real digital twin is just the decision of interface. But we are using the files that have been generated in the virtual world. And when one test file is opened by the digital twin, the output generator are at the moment a COMTRADE file. When the same file is opened by the real twin, the real test set, the output generators are the usual voltage and current generators. So I want you to understand this because it's important. It has to do with the fact that the twins have access to the same data. And now I'm on the minefield because I'm not working for Siemens, but this is a presentation that somehow I've been participating with, so I take the responsibility to what I say, but of course, please contact Siemens for all the details. There is a Cyprotec digital twin. as I told you, and it is a digital replica of the physical Cyprotect 5 device, including algorithm functionality, communication interfaces like, for example, IC6150. It's a full replica. The commentary files that I've generated with my test set is uploaded or are uploaded into the Cyprotect digital twin. So this is my commentary file. The analog signals that you can find in the commentary files are mapped to the analog inputs of the digital twin relay. They use the SMRT voltage 1, A, B, C, and SMRT current A, current B, current C. And I connect to current transformer 1, current transformer 2, current transformer 3, voltage transformer 1, voltage transformer 2, voltage transformer 3 of the protection relay digital twin. Then you click on this button, start a simulation digital twin. You go here and select, it's a little bit difficult to show it on PowerPoint. You select the commentary file you played out, and as a result is available at the virtual HMI for the first analysis. You see trip, fault, distance to fault, whatever you would see on a real relay. In the second analysis, it is possible to assess the test results by using the event recorder and the disturbance recorder. So you connect to this relay with the Dixie, you upload the disturbance recorder, you can measure the trip time, you can see if it tripped according to the correct way, if it is behaved correct, etc. As you normally do, many tests are doing the disturbance recorder also in substation. So if you find errors or configuration, which you will find, they can be corrected from Dixie file. You can transfer the data into the digital twin, and then you can repeat the test until you are happy. And when the result of the test is okay, the same Dixie 5 file can be used for the physical device, for the physical protection relay. What did I say? Again, that the twins are accessing the same data. Is that important? Yes, this is very extremely important. The Megger twins have access to the same data. My test files validated in the virtual world can be used in the physical world. The Siemens twins have access to the same data because I run against the digital twin, I fix the settings, I fix the configuration, and I run it then against the same relay. Otherwise, the benefit, still there would be a benefit in doing this test, but it would be minimum because you have to redo all the job. So no, this is a major, most important issue. And please read this article. This is not for relay protection, but it is showing the interest of digital twin for doing virtual commissioning. And it's only talking about the need that the digital twin must be able to access the same data. And I love this very much because I can say, okay, what can it mean to have access to the same data? Well, suppose I have a digital twin, a robot that does the same thing as I do. I stay home, I send my robot to work. So the robot, my digital twin, will do the job for me, and he will get paid in digital money. But since I have access to the same data, that money can be used for me to pay my vacation to the Azores. So this is now a good example what means to access the same data. You can reuse the data in the digital world for the real world and go to do some protection, virtual protection commissioning for our application. So which kind of test can be done with this? Because you see, we don't stop the test set. The test set is not interacting fully with the, now it's open loop test. We decide and the next step will probably come that we will have full interaction between relay test set and digital twin. For the moment, it's open loop test. Well, but many tests can be still done. Front display functionality, single line diagram, measurements, LEDs. Look that the measurement is correctly shown on the single line diagram. PLC logics like interlockings. They are easy to test, but they're complicated. They're long, but they're easy from the competence point of view, but they are tricky. 6150 signal, have a look at the correct MMS and correct goose message is sent when the correct current voltage or correct interlocking signal is received by the relay, and these signals are given by the test set, digital twin test set. Then you can do, of course, more complicated tests. Is switch on to fault working? Yeah, switch on to fault is a tricky situation. You have some settings under voltage and no under voltage, circuit breaker connection, etc. It is a tricky configuration, can be tricky. Test it and use a disturbance recorder to verify if it is worked correct. Is a relay tripping for a fault in reverse when you should not or you should? Is the inter-tripping scheme correctly designed? Permissive overreaching, overreaching, blocking? All of these things are based also on the fact that you open the event recorder and you look at the results. Weak in-feed logic is also a sort of inter-tripping scheme. Current reversal logic, that is very tricky because there are some timers there. It can be worth to have a look in the detail with the disturbance recorder. And especially keep in mind that if you are running 4 or 5 setting groups, you have to test all of them. So the setting groups are beautiful, but they are bad because you have to test all of them. And once you have performed your tests for the setting group number 1 with small changes, you can perform them for the setting group 2, 3, 4. And you don't have to sit there in the substation to do this. You can do it at home. I think it's a beautiful idea. I hope I'm trying to convince you at least on the possibilities in the future. Correct cycle number. Have you done the correct index? Is not called cycle number. Index is called the compilation time. Have you compiled your extra logic with the correct compilation speed, or you are adding additional time delays that you should not add into the protection logic? This is a typical problem of testing in the substation when you test your configuration, and all of this can be done by measuring the disturbance recorder. So you don't need to go there on site. You can fix things before. And also, remember, what we do when we test, and don't tell me this is not true, the majority of the times we are not testing the relay, we are not testing the test set, we are testing ourselves. Did I understand correctly here? Did I implement the logic correct? And maybe the customer will say, no, this should not happen in this case. And then that is when you in a substation, unfortunately, you need to change something because you misunderstood. So, what is next? Standardization. Don't move if you don't have the feeling that there is a standard watching on you. I mean, today we need to know that at least I work for IC, but IEEE also, and IEEE and IC, they work very much together. So if you know that the standardization committees are interested in what you're doing, let's go on and read the standards as much as you can to verify that you are not inventing the hot water, for example, or trying to patent something that are completely obvious. So standards is an important thing that you have always to keep in mind. And of course, the first thing I did is, oh, what about IC? What is IC doing on digital twin? Are they interested or not? And the interest is huge, but it's also new. There are many preliminary work items, new work items, so proposals, Internet of Things and digital twin. It's not really our stuff, but we have probably to enter into these groups and tell them, okay, guys, we are also in the game. Is there any profile of digital twins we can do for relay protection testing, for example? This is one concrete proposal. If you look at the links that I gave you, they are all preliminary work items, definition of digital twin, how to decide that the digital twin is a real digital twin or not, how to validate how simulation is good or bad. For the moment, it's in the hands of the manufacturers to understand how good we have done or not. So I see it's very interesting on the digital twins. I'm pretty sure in the few years from now, we will see a lot of developments there. We are interested because we're going to save a lot of money, we as relay protection engineers. And in Megger, we have to follow these things, of course, because we do test sets. We have written, I'm very happy to say that, we have just written a peer-reviewed paper for IEEE on digital twin together with our colleagues in Siemens. And this has been accepted a few days ago, so I was very happy that I could put it here, and it will be published soon in October. And this will go a little bit more with the technical details and more higher level definitions of what digital twins are. Tutorial about digital twin. We have probably a demo. We will run a demo with our test set and of course a virtual test set and the virtual relays at the GPECon 2029. See, my goodness, 2021. And it's the 5th of October. Please join this conference if you're interested. I think we can have a very good chat. It's virtual, so you don't have to travel to Turkey. We are going to present. Niklas is going, and myself, we are going to present at IC 61 and 50 week 2021 in Stockholm, but it is virtual event, this one. And the gold sponsor is Megger, so we are going to present digital twin, and I hope our friends from Siemens will join us there as well. And you can see in the links I put that there is a video from Niklas explaining, and from Mandana White, the organizer of this conference, explaining what we're going to do. Now, for more information about Siemens, because maybe I have said something wrong, I'm not sure, but I have been very, very careful in what I said because it's not my field. You have to talk to Cedric Harispuro, who's the technical manager for the digital twin, and I gave you the contacts here. You can contact Siemens as well, and they will bring you to him. And for us, at the moment, the biggest manager for digital twin is participating here, Niklas Wetterstrand, that I also would like to have a few comments from him, if possible. Niklas, prepare you this surprise for you. And again, as it has happened many, many years ago with 61 and 50, where we have developed the test methods that are now used also by many others. Stay ahead with Megger. I hope our others will follow us in the future for the digital twin. And I am finished. I have done it as a promise in 45 minutes. I don't know. I'm ready to take questions if there are questions, but I think I have to say stop sharing.
Thank you, Andrea, for this wonderful presentation. I believe you have answered many questions during the session.
Well, I was very impressed that I got a pop-up message with at least I was handling. It was only a few seconds. Yeah. I was not able to read all the second, but I think I understood the question.
It seems that this question was sent privately to you. I cannot see them.
Yeah. I really don't know. It was a notification that appeared on my.
If you would please just check this question that was sent privately to you and maybe read them out loud and answer the question so everybody becomes.
As I said, is a written ID Scout
the full picture.
Simulate the physical really where no really is the ID Scout. As I said, is simulating the. It's not the only one. There are many other tools that can do that. As I said, ITT 600 and SICAM PAS, they can do that since many years and can simulate. They don't simulate. They simulate the. They simulate the data model of the device. They don't simulate the protection algorithm into the device because the 61 and 50 does not standardize the protection algorithm. It does only standardize that the trip from zone 1 has this norm, that the zone 1 is called PDs. The trip is called PTRC.op or something like this, I don't remember. Start is called ST, for example. But you can raise it up and down, and when you raise it up, because the relay trips, you simulate the relay tripping, but you don't simulate the relay tripping because voltage and currents are generated and the relay is measuring them, calculating the impedance, comparing with the settings, and deciding to trip after the timer. You are just boom, raising the signal, which is okay because that signal will send the goose message, and that is what you want to test. You want to test the goose message. But that goose message with 1 will be sent also if the protection function is blocked by the application with the physical blocking signal 1 on it. You send a trip signal when the protection function is blocked. This is not wrong. It is wrong for me because I want to test the application and the settings of the relay, but from you that are testing the goose messages, it's not wrong. You don't care about that. So the digital twin fills the gap. Only Siemens can create a digital twin for the Siemens relay. Nobody else. Only Megger can create the digital twin for the Megger test sets. And only Omicron, since you are talking about Omicron, can create a digital twin for the Omicron test set. The challenge is in how to define this interface so that on the same screen, I run the test set, and I will not create a commentary file. I will run the test set, play the button, and inject the data to the, in this case, Siemens relay, and then the Siemens relay will trip, and I will stop my virtual binary input, and I give it a trip time. This is not possible at the moment, because we have not defined the interface to go left and right, right and left. But we will work on that depending on the interest. Anyway, still the first step is done. I hope I have managed to explain what will happen if the relay has some error. The simulation might be correct, but the relay may be error. Well, that is the definition of what is a digital twin. If the digital twin is really based on the protection algorithm, I think this will not happen. In our case, for example, I can tell you very often I get a question, how do you validate the digital twin? Yeah, I've been working tightly with the R&D department. That I say thank you to them, all of them, because unfortunately R&D people are never mentioned in these conferences, but without them we couldn't do anything. And they say, hey guys, I have a problem here. It doesn't work. And they come back to me say, no, it works, but it doesn't work. I mean, also the test set doesn't work. So when with the bugs in the digital twin, the digital twin is so well done that the bugs in the real test device are happening in the simulated device, then you are happy the digital twin is a good copy. So this is one factor. Validation of the digital twin is a big job. And of course, you can always have a problem in case it's not validated correct, but it's a customer, not manufacturer responsibility to do validation.
Okay,
Yeah,
thank you for that answer.
Digital twin for Siemens. I have said already too much. Please contact Siemens for this.
Someone is asking, in the digital twin, can you also monitor the assigned digital output for your trip out?
No, not at the moment, but not at the moment. For the moment, we have an open loop test. We do the test, our pre-fall fault test, and for the moment we are doing only pre-fall fault test. But we are working on other tests. All the tests can be done in open loop. And then we create a commentary file. Out of the test plan, we create a commentary file, the output, but the test set runs, I want to say again, the test set runs and spit the data in commentary file that we load and we run on the digital twin. But if the digital twin relay trips or doesn't trip, you have to validate at the digital twin relay level. I cannot connect my binary input test set to the binary output of the digital twin for the moment. I can understand there is a wish for everybody, but everything a step at a time. We are not 100% ready with the technique, but we are on the edge of the technique. So hopefully next year I will tell you something more.
Hopefully. Thank you, Andrea. It seems that we are out of questions for the moment.
Is it possible to have 2 words from Niklas if Niklas is still participating?
I believe he's not in the panelist list. If he's in the attendees, I can just.
Okay, no. Okay, I thought this was possible, so I apologize. I really would have appreciated a few words from Niklas, but yeah, he is not as a panelist, so we cannot do it. Okay.
I think it is possible. Sanjay, would you please just transfer Nicholas from the attendees list to the panelist list?
This is improvised. It's my fault if it doesn't work.
It's okay. We can try. Why not? By the way, while doing so, after this, we will be having a quick break just as a refreshment, and then we'll start with the next session by Mr. Muhammad Ashraf.
Yeah, Ali. Ali?
Yes. In the attendee list, all the attendees.
Yeah.
Just add him as
Niklas Wetterstrand.
Ali, are you there?
Maybe, guys, maybe we can run with the next presentation so that we don't stress a new presenter. Thank you for presenting, by the way. And if we have some time, we can have a few words from Niklas at the end.
Ali, you want Nicholas to be?
yes. Would you just put him as in the panelist?
Okay, wait, I got it. Okay, Nicholas is there, and should I give him the present? Should I make him the presenter?
Oh, I'm here. Magic happened.
Hi. Yes.
Wow. Congratulations. Welcome, Niklas.
Thank you. Thank you. And thank you for the wonderful presentation. It's always a pleasure to hear you talk, Andrea, and you're very passionate about these new technologies. And so am I, by the way. It's really impressive what you can do, even though we just scratched the surface right now. We will see more coming, but it's really, really interesting how we can improve things for substation engineers.
So, Nicholas, you are the present. You need to present now.
I don't have a presentation. I'm not really sure what Andrea wanted me to say, but I thought he just wanted to let me in and say a few words about this. Or did you have something else in mind, Andrea?
No, exactly. I just wanted to present you because you are the top manager dealing in the Megger International Group with us from Sweden and our colleagues from United States, and we are under your umbrella. So I thought it was nice to hear 2 words from you that are dealing and driving us into this travel. And maybe you will drive us also in other travels in the future, but not, for the moment is one of the top travels we are doing under your guide.
Yeah, okay, thank you. So I'm the business development director for protection within Megger. That's what Andrea referring to. So I'm holding everything within the protection circuit for the substation, which of course includes relay protection, but also high voltage circuit breakers and instrument transformers. But this, again, it's a very interesting subject. And as Andrea pointed out, there will be more. We have already the electrical tester article out, which a few colleagues of mine, including Andrea and Siemens colleagues as well, have written. And we also have presentations upcoming in GPCom and IEC 61850 week. So please join us, since it's all virtual, it's fairly easy, and you will be included in more interesting discussions around these topics. And I think that's it, so we don't screw damage your time schedule.
Thank you, Niklas. Appreciate
Thank
it.
you, Andrea, and thank you, Nicholas, for your contribution to this event. We will be taking a short break for 10 minutes. I'm sorry, Mr. Muhammad, I will be taking 10 minutes from your session just as a refreshment and have a start fresh in the next session after 2 sessions back and back. So we'll see you after 10 minutes exactly. All right, welcome back, everyone. Our session today is about traveling wave and time domain based protection schemes. It will be presented by Mr. Mohammed Ashraf. He is a colleague from Schweizer Engineering Laboratories. So, Mr. Mohammed, the floor is yours. Please feel free to start whenever you like.
All right. Thank you very much, Ali. I hope you can see my screen and my audio is clear.
Everything is clear.
Okay, thank you. So thank you very much for Megger team and all the participants who have joined us today. So in this couple of days, we talked about some innovative solutions and some new technologies that we can use to get some more benefits and to take care for the challenges that we have for the modern protection systems or modern power systems. So this is Mohammed Ashraf from SEL. I'm application engineer based in Saudi Arabia. And today we will talk something about some new technologies that is a little bit different from conventional phaser-based technologies or methods that we use for the protection schemes. We call them as time domain based technologies. So the advantages is they are much faster, and they are they can take care for the challenges that is we have with the modern protection systems like renewables, inverter-based injections, and these kind of challenges that we face with the conventional technologies. So we have some modern solutions to take care for these kind of challenges. So first, we will just understand the concepts that what does it mean by traveling waves. And there is one more methodology. We call this as incremental quantities, TD quantities, and TW quantities. So first, we will just understand the basic concepts, and then we will try to link these basic concepts with applications. That is what we can achieve with these two methods or technologies. Conventionally, we are using differential protection for our lines or transmission lines of the cables feeders. So we have a new differential element based on the traveling wave. Similarly, we are using some permissive schemes to protect our lines. That's the directional permissive schemes. So we can use the new technologies to achieve the same conventional things, but with more reliability, with more speed. Distance protection is being used to protect the lines from a very long time. So we have some innovative advancement in the distance elements that makes the distance elements much faster as compared to the conventional elements. Apart from protection, we have some other features that is kind of a future of power system protection. We call them as asset monitoring features or line monitoring. So these features are not available currently in the available IEDs or protection relays that is we have for the line. So either we need to depend on some dedicated devices, or we need to depend on visual inspection or preventive maintenance to detect some kind of incipient faults or the faults that haven't happened, but these are going to happen in the future. So line monitoring is very important, and it will tell you some weak points in the overhead lines or the cables that are susceptible to be failing in the future. So it will help you in predictive maintenance as well. Auto reclose closing is one of the applications that we can achieve from these technologies. It is also useful for especially for lines with some challenges like tap loads, hybrid configuration, like some part will be overhead line or some part will be underground cable or a combination. And similarly, one of the most challenging thing is the fault location. So fault location for transmission lines is one of the challenges that's been in the past. So it is a little bit solved by the distance relays that they can have some impedance-based methods, and you can just have an idea where the fault is, but still it's not that much accurate. You have to patrol the line maybe 5% or 10% to get the actual fault. we have a traveling wave fault locator, which is much more precise than the conventional distance or impedance-based methods. And you can trace the faults, or it can identify the faults with one tower span, that is plus minus 300 meters. So these are very crucial benefits that you will get from traveling waves and incremental quantities in terms of security, sensitivity, speed, and the fault location as well. So it will save a lot of cost on the line monitoring. So you can just avoid the outages in terms if you have the preventive maintenance schedule for a line which is having a problem or a potential problem. So you can save a lot of money, a lot of expenses on the outages, and also for the fault location, you don't need to patrol more portion of the line. So it will save a lot of man hours, a lot of inventory in terms of economy. Okay, let's talk about traveling waves. The concept of traveling waves is not new. It's been understood, and it's inside. It's like a theory that's been is maybe 50 years old, but it's just analogous to, for understanding, you can think about stagnant pond of water, and you just drop a pebble in a stagnant water and it creates some concentric waves. So these concentric waves will travel from the point of disturbance, and they will be distributed evenly, and they will travel away from the point of disturbance. The most important takeaway from this example is the traveling waves will be much stronger at the point of disturbance where you drop the stone. And once they travel towards the edges, or once they travel 360 degrees in all the directions, their amplitude will decrease. So these are the two important takeaways, and that the concept we just correlate with electrical systems in a way that whenever you have a disturbance, you have a kind of very minute transitions or high frequency components that's just happening at the point of fault. And after that, you may have a steady state fault current that may be more, and you can just detect with the phasor-based methodologies, the conventional methodologies. So traveling waves will be important, or the application will be utilized in a very fast manner, maybe in few milliseconds. You can just think about less than quarter of a cycle, traveling waves will die down. As you can see over here, there's a very high frequency transient over here, and it dies down over here. So within few milliseconds, they will die down. And the phasor-based technologies, which are based on sampling the data at a slow rate, so they're not able to catch these very high frequency transients over here. So this is one of the principles that differentiates the conventional phasor-based technologies with the traveling waves. So we will be just getting some decoding the information or the trend that we got from this region, and making the decision very, very fast. Okay, how it works, just to have a concept, just as we drop the pebble in a water, similarly, if you have an insulation failure, or insulator has been broken due to aging or due to some external factor, so it may touch the ground. So this is a very simple example that one phase is just the insulation has got breakdown and it touched the ground. So we have a change in the voltage or the disturbance. So that is, we can consider it as phase to ground voltage. From its peak, it went to the ground immediately. Just consider it's a bolted fault. So we do have relationship that we can find out the change in the voltage if it is a 230 kV line. So, and we just assume that the fault happened just on the peak of one of the phase voltages. So the change, we can just derive it as, estimate as 188 kV. Conceptually, whenever there is a fault, there will be a traveling wave that will be originated from here, and it will travel, same as in case of water, in both the directions. Water is 360 degrees, but in the line, you have only two dimensions. It can go in this direction, that is reverse side, or it can go to forward side. So whenever there is a disturbance, or we call this a change in the voltage, so it will be traveled from this side, from the point of fault in both the directions. So this is how it travels. So once it travels from the point of fault and it reaches the station on your left and the station on your right. And one more important thing is it's not only the voltage change. So whenever there is disturbance, there will be an associated traveling wave in the current as well. So we call this as current traveling wave. So there is a simple relationship between voltage and current. We can just find out the traveling wave or the disturbance in the current with Ohm's law. That's voltage divided by the impedance. So ZC is basically your characteristic impedance of the conductor. That is a known quantity depending on your conductor. Mostly for overhead lines, it's the range of this characteristic impedance is from 200 to 400 ohms. So for that particular line, so you can just assume and you can estimate a step change or disturbance in the current as about 670 amps. So we'll be getting two quantities at both ends, which will be disturbance or the change in the voltage and also in the current. The next important thing in the traveling waves is the time taken by that disturbance to travel from the point of disturbance to the stations. So it depends on the line length, because all the waves have a speed, and the distance will decide that when the wave will travel and reach the station S and when it will reach the station R. For example, a fault happens at a quarter of the line from station S and 3/4 from station R. So once the fault happens, a traveling wave will be generated on both sides. So it will reach the station S earlier than at station R. We are talking about microseconds. So the time taken by a traveling wave to travel from this point to station S is Ts, and the time taken by this traveling wave from the point of disturbance to station R is more. Now there is one more parameter that is we call this as traveling wave line propagation delay. This is very important. If we have this value, so we can just find out the time reference, and we can just exchange some information between two end relays to get a lot of things out of it. Maybe a traveling wave fault location or differential protection. We can get a lot of things if we get all this information. So traveling wave line propagation delay is kind of a fixed parameter. So it is defined as the time taken by a traveling wave to travel from one end to the other end of the relay, to the other end of the feeder. So there is a way to estimate that one or calculate that one, because these traveling waves are electromagnetic waves, and we can compare them with the speed of light. So for overhead lines, their characteristic speed is 98% of the speed of light. They are very, very fast. You can just consider if they are traveling at a speed of light in overhead lines. And for underground cables, their speed is much slower as compared to overhead lines because of the properties of insulation and the cable properties. So it's 55% of the speed of light. So we know the speed, we know the distance, that is our line length, maybe 300 kilometers in case of overhead line. Then we can find out the time, which is our time taken by a traveling wave to travel from one end to another end. So this is a constant that we can estimate as in microseconds, like about 1021 microseconds is the time taken by traveling wave to travel from station S to station R. Similarly, if we have an underground cable of the length 42.2 kilometers, so the time taken by the traveling wave or DWLPT is 255 microseconds. So this is a way to estimate it. We can calculate. There's another way that is we recommend to do is to actually measure the traveling wave line propagation delay. So we call this as line energization test. So we do a test on the line. So we open the remote breaker and we just try to close the local breaker. Once you close your local breaker with the remote breaker open, so it will create a traveling wave because there is a there's a switching action. So line is getting energized, it will be getting some currents and the voltage as well. So there will be a disturbance or a traveling wave will be generated over here. That traveling wave will travel to the remote end, and it will be bounced back. There's a property of reflection for all the traveling waves because there is a change in impedance. So once if that end is open, so that traveling wave will be bounced back or got reflected from this end and it will come back. Because we have a very precise time measurement on this relay. So it can measure the time when it's generated over here and once it's come back. So if we have the information on these two times, so the relay, from the relay event records, we can capture the round trip delay. So the time taken by the traveling wave to travel from this end and coming back is called a round trip delay. And if we divide that round trip delay, we can easily find out what is the time taken by a traveling wave to travel from your local station to the remote station. So this parameter TWLPT can be measured with this test much precisely. If you cannot do that, there is a previous method you can estimate as well. So this information is also required to calculate very precise fault location. All right. The first element that we're going to discuss is a differential element that is based on traveling waves. So we can just consider a fault that is external fault that is not in the line. So we can just consider a traveling wave that's entering your local end with one of the polarities, say positive polarity. And once it travels along the line, it will reach the remote end as well. And the remote end will see it in a negative direction because of the CT polarity. So this is just like the current entering over here and the current leaving from the remote end. So the traveling waves recorded at both ends, you have opposite polarities. It's positive on the local end and negative on the remote end. And one more important thing is the duration or the time reference between these two traveling waves capture time will be separated by line propagation delay, which we have measured before. So a traveling wave will enter and it will leave the remote end after this time. So if we have these two things in place, opposite polarities plus the peaks are separated with line propagation delay, it is a clear indication that the fault is external. We do have some current supervision as well, but the basic principle to detect any kind of external fault is this criteria. Similarly, for internal faults, we use some Clark transformation parameters like alpha and beta components of the three-phase components, three phases currents. And the principle is very simple. If a traveling wave is created by an internal fault, so the local end will see with one polarity and the remote end will see with the same polarity, just because of your CT configurations of the start points. And the time between both the relays, that will the time of interception of this traveling waves will be less than the line propagation delay, because you can just consider a feeder and the fault just maybe in the middle. So it will the traveling wave will definitely take less time than the total TWLPT time to reach both of the ends. So this is again linking the concept with the application. So positive peaks are the same polarities and the time less than the characteristic or the fixed or the constant time. So this is a clear indication it's an internal fault that, and in this principle, your TW87 will detect or will decide whether the fault is internal or external. So the only thing that is creating some delay in this process is the communication between the relays. So for this particular application, we need a direct fiber between both the relays so that they can communicate in a very fast manner and they can exchange the information, because local relay will need its own information as well as the remote relay information to decide whether it's internal fault or external fault. So TW87 will be needing a direct fiber communication between both the relays. Next is the element, which is, we call this as a directional element, and it uses voltages, traveling wave voltage and the current as well to decide the direction. So these elements can be used in permissive schemes along with some other supervisory elements, as we call incremental base directional elements. And just consider a fault over here on the right side of your screen. And you can just calculate the traveling waves in the voltage and the currents with that relationship. So once it travels along the line, so they will reach the station. And once they reach the station, depending on the CT polarity, so the relay will detect the traveling waves and the current in negative direction if the fault is in the forward direction. So if you get the polarity of or the change in the voltage and currents in an opposite fashion, similar as our directional concept, so it will be decided as a forward fault because the polarities are opposite. And similarly, once you have a reverse fault, so you'll get both the things in the same polarity. So this is just like a polarity comparison, and this is one of the fastest elements available for the directional decision. One more application for this traveling wave is the fault location. So we have two kinds of fault locations available depending on how many relays you have in one feeder. If you have a relay only on the single end, we call this as a single end traveling wave, and it will not be taking or connected with a remote relay. So if you have only one relay at one of the ends of the line, so you can implement traveling wave fault locating, that's single-ended method. This is still better than impedance-based method, and how it works is pretty simple. Whenever you have a fault on a line that is at the point M along the line, so it will create it will launch the traveling waves. So the traveling waves will travel to point S, and they will also travel to point R, because we don't have any communication with the remote relay, so we are not we cannot take the information from the remote, so we just have to rely the local traveling waves. So once it travels and touches your point S, it's at the T1. The relay will just time step that point, and after the reflection, it will go back and it will hit that fault point again. Hit that fault as a change of impedance, and it will travel back. So if the traveling wave is stronger, so it can come back and it can bear one more reflection and it can come back again. So if the relay knows or measures the time T1 and T4, so with that empirical relationship, you can find out or you can solve that equation for the value M, which is the faulted point from the station S. So if you know T4 and T1 with that reflections, the relay can give you easily the information on the fault point. This is much more accurate, and it is not dependent on the remote relay communication. So this is one of the methods that we use for to detect the to detect the fault location precisely if you don't have a connection between two relays or if you have a single relay. Another method is much more reliable. It's called double-ended traveling wave fault location, in which we will be using the data or the point at which the traveling wave strikes at station S, and also we have the information from the remote end. So these relays should exchange some data that when they have seen the first traveling wave. So for example, it has touched, the traveling wave has been intercepted by point S or station S at time TS and TR at remote end. So if remote end gives the information to the local end that I have seen the fault at time TR, using that information, local end can find out the distance M, which is actually the distance from your point S to the actual fault. So with that relationships, if you have the formula for M and similarly for the other line segment that is after the fault, and you can just solve these two equations and you can find the value of M, provided you have these two times, TS and TR. So TS is the time recorded by your local relay, and you should have the data or the information from the remote end as well. And you can just use that values, and relay will give you a very precise fault location for point M. All right. One more application that is we can get out of this modern technologies is auto reclose control or auto reclose cancel logic. In some hybrid applications where we have overhead line and some underground part, or maybe have some more sections of overhead and underground, or a combination of that. So there is always a challenge to block the auto recloser for the portions of underground cables. Or maybe there's a tap off line somewhere over here, so you don't want to auto reclose in that location. So this is a challenge for conventional distance protection, and either you will block it, or you will just compromise on the selectivity. So we have auto reclose cancel logic, where the relay can pinpoint or block the auto recloser in that region where you want it to be blocked. It uses a double-ended fault location method, because whenever a fault happens in that particular portion that you have already defined, so the relay already knows the fault location precisely in that location, and you can just define with the tolerance that portion to block the auto recloser. And auto recloser, it can be external, so you can just send a blocking signal to your external auto recloser, and it can you can control it according to the fault location. It is applicable for hybrid lines, tap lines, and also it's good for the series compensated lines if you have capacitors. Okay. Apart from protection, we have some innovative advantages from this technologies is line monitoring. We have, or we call this as asset monitoring. So this is maybe because of some extended vegetation, some plants or some trees grows, and with the passage of time, they're going to touch the transmission line, but it's not a fault. It's just like a fault that's going to happen in the future. Some failing insulators, the insulators may have not failed completely, but there is a kind of discharge or some kind of low energy events that's happening because of insulator bad insulation. Also, some dirty insulators can cause some low energy events on the lines that may cause the insulator to fail in the future, and also the bushfires. So in the relay, we have line monitoring element, which is again using the double-ended traveling wave fault locator. This is the most effective method to pinpoint where you have the low energy events, and the relay will divide the line in some sections. For example, you have 100 kilometers line, so the relay will divide the 100 kilometers line in sections of quarter of a kilometer, like 0.25 kilometers, and it will just make segments or bins, and it will monitor each bin at all the times. Whenever you have some faults, a disturbance, or low energy events, so there is a counter. It will keep on counting, and it will incrementing that counter to predict if there is any incipient fault in that location. So once the counter is up to, it is count up to the value. For example, the count you set as 5 events in 24 hours. So once that counter is counted up to 5, so it will give you an alarm. So you can send your crew to that particular location for the inspection to the preventive maintenance. So this is saving a lot of cost for the actual failures you have, or the actual outages you will have that will be unpredicted. So this is something that is a kind of a future of the power system, where you don't need to patrol all the line all the time. And this principle or this element will help you save a lot of cost. Next is the concept is kind of incremental quantities. So before we have seen the traveling wave and the advantages of traveling waves and some applications. So now is the time to discuss a little bit on the incremental quantities. We call them as TD quantities as well, time domain quantities as well. So the major concept, to simply understand incremental quantities, is just like a faulted circuit. So what the relay will measure will always be a fault current and a fault voltage. The primary intention behind to solve this faulted network is to divide in 2 networks. We call this the first one as a pre-fault network, because the relay is measuring the pre-fault as well. So we can just break that network in 2 networks: a pre-fault network, which is a healthy network, the normal one, and a faulted network. with no source, but just a source, or you can say a faulty source that's available at the point of fault. So if you just see at the black waveform, and you can consider this as a waveform of the fault. So black waveform will just divide in two parts. One is the blue, which is the pre-fault, or the healthy currents and voltages that were flowing before, and the one which is a change. We call this delta quantities or incremental value quantities. So the changes, what happened due to the fault is delta V and delta I, and these are the pre-fault quantities. So all of our discussion in the coming slides will be on the changed quantities. We will not look what the relay has measured or what is the pre-fault quantities. So whatever is a change, we can use that values to get some elements that is much faster and much more reliable. Okay, it has also two elements. One is the directional, and then the next one is the distance that we will discuss in the coming slide. For directional quantities or directional decision based on the incremental quantities, just consider a fault in front of the relay. So we have a relationship that is whenever you have a fault in front of the relay, so relay will measure an impedance behind it. That is basically essentially the source impedance, the reactance and the inductance, and there will be a change in current that will be in opposite direction, or we can call this the negative polarity. So this is the principle. Whenever you see a voltage that is opposite to the current, it means it's a forward fault. Similarly, for the reverse fault, if you have fault on the backside of the relay, so the relay will apparently see an impedance that is in front of it. That is the line impedance plus the remote source impedance. So this is a constant, and the current direction or the polarity will be the same as voltage. So just depending on these polarities, we will be deciding whether the fault is forward or reverse in reference to the position of the relay. So this is the same concept as conventionally we are using, but here we are using the change in quantities. It's delta V and delta I. And there's a bit difference that we are using the actual quantities in the relationship is we call this as incremental quantities loop replica currents. So these are derived from delta I. There are some relationships that you can derive the loop replica currents from the change in currents, but these are both are analogous. So you can just for the simplicity, you can just consider delta I is the same as delta IZ. The deciding factor here is the polarity. If they are in opposite in polarity, it's a forward desirable. If change in the voltage and change in the current are in the same polarity or the same or in phase, we decide it as reverse faults. Next is a distance element, which is based on incremental quantities. So just to understand the distance element, we will just consider that there's a fault on the reach point because this is an underreaching zone. It's not 100%, maybe set as 70% or 80% of the line, similar as our instantaneous zone that we are setting in a distance element. So at the reach point, if you just consider a fault over here, and we are somewhere on the waveform, whenever this fault happens, and considering this as a voltage fault, so you will know this fault is a voltage that is a pre-fault voltage, and it will die down or it will go to zero immediately with a change in the voltage. So this we call this as a reach voltage. So relay is estimating or calculating the reach voltage for each fault, and it is compared with your setting. So that's coming in the next slide, and the relay will be using the change in the voltage and the change in the current. And remember, this is not phasor based. We are just taking the samples on the waveform and we are comparing with the previous sample. So for the phasor base, you need to wait at least half a cycle or full cycle to convert that into the phasors and do the actions. That's why it's much faster as compared to the phasor based, because we are not dependent on the phasors. All right. Let's consider a fault that is within your reach. This is your reach, and the fault is happening within the reach. So if the fault is within the reach, so it means it's much closer to your source. So the changes in the voltage and current will be stronger, and the relay will estimate or calculate a voltage change at the reach point. Apparently, that calculation will be higher than whatever is your pre-fault voltage that the relay is watching before the fault. If this is the scenario, the relay will decide it as an internal fault or in-zone fault. Similarly, if you have a fault that is away from the reach point, so the changes in the voltage and the current samples will be such that the impedance that it will the voltage change that it will calculate will be less than the pre-fault voltage. So this is a criteria that how we define it or how we decide it as an in-zone fault or an out-of-zone fault. And this is not phasor based, so that's why it's much faster than the conventional distance protection relay. One more application we have that is special for the series compensated lines, because series compensated lines are always been a challenge for the conventional phasor-based technologies because of the impedance compensation. The relay will not get the real-time impedance of the line because of the capacitance. So we do have, just consider an example without series compensation settings. So if you have configured the relay without series compensation, so we have some operating region and restraint region. So the operating region for this TD21, and these are all internally calculated operating and restraint quantities. So this is like operating voltage, and this is the restraining voltage we have. So it's just like a concept that we are transforming the TD quantities in this plane. So we do have some operating quantity, operating region, and some restraint region. So in case of an internal fault, the voltage collapse or the operating quantity will just enter your operating region. And if you have another event like voltage increase due to switching or lightning, so the operating quantity will go in other direction in the restraint region. So it's inherently secure. And we have added another security for series compensation. You can just consider this as an operating region. And for the series compensated lines, we have this kind of characteristics, which is much more secure. So we have trimmed that area and we have included that in the restraint region that was before in the operating region. So this will add extra security for series compensated lines. Either maybe the series compensation is inside the line, or maybe it's external to the line. And also it will be immune from the capacitance effects because it is sample based. So it is much faster from the capacitance response as compared to the phasor based technologies. All right. So all the elements we talked before are combined in a device. We call this as SCLT401L. It's been launched last year. It's basically a variant or an advanced version of SCLT 400L that was launched 3 or 4 years back. So this is kind of a solution which will provide you the modern technologies, traveling wave, incremental based technologies, plus the conventional phasor based technologies. So it's basically a combination, and you can use this as a standalone line protection relay for any kind of fault, for any kind of feeder. It may be an overhead line, it may be a hybrid, or it may be a combination. On special applications like inverter-based generations, it may be hybrid installations, or maybe multi-terminal applications compensated as well. So it is having the newer technologies with the phasor-based as well. And fault location guaranteed to 1 tower span, that is we guarantee plus minus 300 meters. And auto reclosing control that you can have a very innovative auto recloser control if you have hybrid line applications. And the sampling is 1 megahertz. This is something that makes this relay different from the conventional technologies, and TD and traveling wave protections possible because of this very high sampling rate. It can be used as a line monitoring feature, as we discussed, to detect some incipient faults, or the faults that are not happened or they are about to happen, or we call this precursors or incipient faults as well. And it's a modern relay for modern power systems because of the new induction of renewable energy, or the sources, inverter-based sources. So we have some challenges with the conventional protections because of low fault level current. So these new technologies can help in that. And this is the relay which is made from a blank piece of paper from scratch. So it has nothing to do with the conventional relays or other relays that is we are already having the line protection. So you can use it as a set 1 and set 2 because both are based on absolutely independent algorithms and hardware. And it's the simplicity is the core. So we have reduced the complexity in terms of settings, and in terms of logics as well. So the user don't need to worry much about the logics or a lot of parameters you need to set. So this is the functional diagram in which you can see some conventional elements, phasor-based, distance, power swing elements, load encroachment, directional elements, phasor-based, 51, backup overcurrents, and some voltage features. And the new technologies as well, like TW87, TD21, and the directional elements based on incremental quantities and traveling waves. And similarly, we have fault location that is using the double-ended or maybe the single-ended traveling wave fault location methods, plus the conventional impedance-based methods are also available. Line monitoring and auto recloser control. So these 5 elements are the core to the modern power systems. All right. And then you can have standalone or direct tripping with this incremental quantity distance element. It is not dependent on any kind of communication with the remote end. So you can just independently apply this one and it will provide you direct tripping. Permissive tripping you can get with some POTT or comparison schemes with the help of these 2 elements, which are much faster in performance and they can act in few milliseconds. And last but not the least is the differential protection that's based on the traveling wave, but you need a direct fiber between both the relays to achieve this. A little bit on the time comparison or the time performance of the relay. So TW87, the differential elements may act upon in 1 to 3 milliseconds. Plus, it depends on the line length. If your line is very, very long, like more than 300 kilometers, so you can add just a couple of milliseconds more in that time. But ideally, it should operate in less than 3 milliseconds. It's very consistent. TW32 is much faster, even it responds in 0.1 seconds. So you can just think about 0.1 seconds as compared to the normal directional elements. This distance elements are much faster than the conventional distance elements. They respond in from 2 to 6 milliseconds, depending on the fault location on the line. If it is closer, it will act upon faster. And if the fault is away from the relay, so it may cause take a little bit more time. Another directional element that is incremental based is also very fast, and you can implement these 2 elements in your POTT schemes for a very reliable and fast permissive schemes. So this is a kind of graphical representation for permissive source to impedance, half of source to impedance ratio. So you can see TW87 is the most consistent. It's at 3 milliseconds, and POTT schemes are also pretty much faster depending on the channel that you are using. So if the channel is slower, so that time will be added. And TD21, it's again dependent on the location of the fault. So for up to the mid of the line, it's much faster, and you can achieve like 4 times faster as compared to the conventional distance element. There are a few real-time events that we recorded on the lines. There's one line of the utility PNM in Mexico. There's a 345 kV line, and we have captured some current waveforms or voltage waveform, and this is the response of the elements. So the trip happened in 1.56 milliseconds. You can just compare this one with the normal or conventional technologies, taking 1 cycle or 1.5 cycle to decide and trip. And the distance element responded a little bit late. Direction elements are faster, and TW87. This is basically causing the trip. So that's 1.56 milliseconds, and it's 109 miles or about 170 kilometers line. And the total fault clearance time is just the breaker time, because 1.56 is just negligible as compared to the breaker time. So if you have a 1 cycle breaker or 1.5 cycle breaker, so you can just consider the breaker time for the total fault clearance. So you will be having a much faster fault clearance. It means it is adding in the system stability. The faster you clear the fault, it will add stability to the system, and you will be having more power transmission capability, and the system will not go into some unwanted swings or disturbances. If you are interested to learn more about the real world event records, you can visit our website at that link, and there will be many. There are many field results that's this relay been in the service from 4 to 5 years. So we have lots of real-time events, and we can have some performance comparisons with the conventional relays. So you can see a lot of benefits reports over there. Okay, lastly, just I need to give you, because this session is mostly related to the testing. So we have a kind of tool inside, because this session is software and inside the relay, to simulate your real-time faults inside the relay without using any test set. So this is kind of a tool that you can use any kind of event records from your relays. It may be SCL relays, it may be non-SCL relays, some high sampled COMTRADE files if you have. So there is a utility inside our software that will convert it to a file that is compatible with the relay. So you don't need apparently a test set to evaluate or to study any event record. So if you have the COMTRADE from the field, so you can just use that utility. We call this as event playback utility. It will convert it and it will send to the relay, and the relay will itself simulate that COMTRADE data that you have. Originally, it is using the ADC data, but in the event playback mode, it is just switching to your file, which is you have just loaded as a COMTRADE file. So the relay will evaluate all the currents and voltages and take it from that COMTRADE file, and relay will do its decisions. And you can compare these decisions with the relay at the field, and you can just compare how fast is T401L as compared to the relays that's available in the sites, and also how much dependable it is. So this is kind of testing facility available inside the relay without using any test set. And that's all from my side. If you have any questions, so I'll be happy to answer. And thank you very much for your time and attention.
Thank you very much, Mr. Mohammed. That's a really wonderful and very informative presentation that you showed about traveling wave. And before we go to the question segment, I'd like to add that I had the pleasure once to actually test one of your relays, and I was amazed by the result that I saw from the tripping times. It was in just single digit for tripping function, which is something I never seen before, and in some cases even less than 1 millisecond for tripping. So
yeah,
keep up the good work.
thank you very
Okay.
much.
Let's see some of the questions that we have here. We have first question is asking about, is traveling wave fault locator will work on 3-line schemes?
Yes. So as I understood from the questions, it maybe is talking about 3 terminals. So maybe you have one line and one tap off line from the main line. So you have like 3 stations connected with one line. So yes, that's working. We call this as a multi-terminal application. Yes, it can work on the multi-terminal application as well, because we have single-ended fault location based on the traveling wave that is not dependent to communicate with the remote relay. So we can still use that methodology for the single-ended methods as well.
All right. Another question is asking, what is the benefit of using ultra-high speed relays if the breaker will need 2 to 3 cycles to operate?
Yes, that is an interesting one. Actually, the total fault clearance time is a combination of relay operation time plus the breaker operation time. His question is very interesting because we are claiming it, the relay part that the relay is doing before maybe in 20 milliseconds, we are claiming it to be 2 milliseconds now. So we are doing our job much better than before. So we are reducing the time by 10 times. But the problem is on the breaker end. So unfortunately, we cannot control that breaker times if you have existing installations. But in the modern breakers, they are they are claiming, or the performance is much better than 2 to 3 cycles for high voltage and extra high voltage lines. You may find 1 or 1.5 cycles breaker time. But again, if you still have like 3 cycles breaker and a relay which is taking 1 cycle to make a decision, so total 4 cycles you need to clear a fault. With this relay, you may be able to clear in 3 cycles. So there is a study like the fault clearance. If you have a fault cleared in 4 cycles as compared to a fault cleared in 3 cycles, so it will be much better for the system stability and the transmission system power transmission capability. For each millisecond that we save in the tripping time, it means for a bulk system, it is saving 1 megawatt. For each millisecond, you are saving 1 megawatt in the transmission capability. You can think about saving 1 cycle means 20 megawatts more capability on that line, and it will save you from system stability issues as well. So this is one part, like the faster is the better. The next part is we have some very precise fault location. This is not only, we are not talking only about the speed. Now we are talking about fault location, that's plus minus 300 meters. So you can just imagine how much you are saving on the cost of patrolling the line. With the impedance base, maybe you need to patrol 15 kilometers of the line and your 100 kilometers line, total length. With this fault location method, you have to patrol only maybe half a kilometer line. So you are basically saving on other sides. Apart from that, we have line monitoring features now. So it will tell you some very important information on asset monitoring and anything that is going to happen in the future. So it will save your outages. It will save your either it's for the human safety. It's very much important because maybe a line is damaged and it's falling on some causeway, on some roadway, and it may it's like a hazard. So there are like a lot of benefits instead of the speed as well. So speed is one, but plus there are a number of benefits that you will get with these new technologies.
All right. It seems that we are out of questions.
No, I had one.
Just one just came up.
I
as I was speaking.
steal the microphone because I was not able to send it, but it was always great. And maybe because I'm a panelist, but I don't know if it went. Anyway, thank you for your presentation. Very incredible. Of course, there is always, like in digital twin 61F, there is always questions. We are a conservative branch, but I think that the future must look in other methods to measure, and this is another one. So I'm impressed. And the solutions will come and applications also. They're already there. My question to you is on the last slide. I am a little bit interested in that you have shown. You have a sort of a digital twin for your relays?
Unfortunately, I don't have the concept of digital twin, but actually it's kind of a utility, or it's kind of a utility that you can use to test to validate the functions or the results of the field results. For example, there is a field relay that has operated on one of the disturbance or faults, and it has created a fault record. But you doubt the performance of the relay, the speed, selectivity, or any other issues. So you want to validate that, like you want that information that's given by the field relay with SEL T401L, because T401L is not a phasor-based relay. It is having phasor-based technology plus traveling wave and time domain as well. So if you want to evaluate a field event that's from a relay, which is a phasor-based relay, the SEL or non-SEL relay, and you want to validate the response of traveling wave and TD-based technologies on that one. So it's a very good utility. It's a very good tool that you don't need a test set to run or play back that event on the computer to inject that relay. So this is like we can just load the computer files into the relay, and the relay will be playing them. And you can find the results for the protection functions, how TW behaved for that, how TD21 behaved for that, and how the phasor-based protections behave for that. So we can just have, you can say, a study or a kind of a validation of the results given by the field relay, as compared to whatever the new technology is saying about that. So it's kind of a comparison.
So yeah, it is. So the relay algorithms are implemented and are simulated in the correct way, and you are eating the samples
Yes.
in your time. So
Basically, it's using the
it
real-time
looks like
data.
very much you have done
Real-time
digital
data
twin.
means, yeah. So it's using the real-time data, whatever the component you will load. So the relay will internally change the path before, like normally it's taking from analog to digital converter, but then it switches to the component file, whatever you load.
But
So
that
it will
relay
use
is
the
a
same
physical
values.
relay. That relay is a
Yeah,
physical
it's a
relay.
you should have. Yeah, you should have the
It's a
physical relay with you.
relay.
It's not a
Okay, no,
software.
then it's not a
The
digital
software
twin.
you
I
use,
understand.
yeah, the software you use only to convert the component file in a special format. We call this as PLY extension. So that's a playback file. But you need a physical
Yeah,
with
okay.
you.
I understand. It's not a digital twin. I thought that this one was a PC application or in the cloud or in.
No, this is
I
not.
don't
This
know,
is not
it's a
virtual. This is you
full
should have
relay.
the
Yeah,
hardware with you.
it's hard physical. Yeah. Okay. Thank you. Anyway, great.
Thank you very much.
Thank you
I
for
can see one more
participating.
question. That is about using the traveling wave implementation for the distribution system. Yes, there is no limitation on the voltage level. You can implement these technologies in the distribution, sub-transmission, transmission, or even extra high voltage lines. So absolutely, there is no voltage limitation for that. So you can even apply for medium voltage as well.
All right, actually, I do have a question from my side as well.
Sure.
You mentioned that the traveling wave, when a fault happen and this wave travel, I believe they lose attenuation throughout the length of the line. So is there like a practical maximum limit of the line length for traveling wave technology?
Apparently, no, because just for one element, that is traveling wave differential element, we use a direct fiber. We need a direct fiber between both relays. So what we support now is up to 200 kilometers for that particular element. All other elements, you can achieve it through multiplexers and other things. So there is no practical limitation for other elements. But for only for TW87, the differential element that's based on traveling waves, you should take care about the line length. So 200 kilometers is the one. If it is more than 200 kilometers, maybe you need boosters or some other intermittent devices to boost the signal. So that is also possible, but we need to see the feasibility for that.
Right. I believe we reached the end of time for our conference here today. I will leave the session maybe open for a few more minutes in case anyone have any additional question related to any topic being discussed today. Please feel free to ask this question. For anyone leaving us, please note that the recording and also certificate of attendance will be sent to you in 1 or 2 working days by our marketing teams. I would like to thank you all for joining us today. Please don't forget to give your feedback after leaving this event. And also, I would like to thank all the panelists who have contributed in the success of this conference. We are conducting a similar one next week for the transformer segment from Megger. Please feel free to register on that one. The link have been shared on the chat window as well. If you have any interest to that, please make sure you register there as well. So if anyone want to have any questions, you're also thinking of opening the mic. If anyone of the participant as well want to speak rather than type in their questions, please feel free to click the raise hand button, and we will maybe enable the mic for you to speak directly and ask your question.
Yeah, I have a proposal more than a question, if I can, or Miklas.
I'm here.
Okay, I go on. I see it. Can you hear me?
Yeah, I hear you.
Okay, all of you. My proposal is that we have here a group of many people. I have lost the page with the number of people, unfortunately. But anyway, there were more than 96 people today and more than 110 yesterday. It would be nice if we could share our LinkedIn addresses so that we grow our network, and we know that there is a network with the people that have the common interest. I try to search many of you, and many of you are not even on LinkedIn, or maybe the name is spelled differently. So it would be nice if we could share the LinkedIn addresses somehow through you guys organizing these events.
Yeah, sure. We can, in the certificate email, send the LinkedIn for every panelist that we have today. And if you would like, please feel free to just to drop in a link in the chat now.
But the
For your
chat,
LinkedIn.
the
Yeah.
chat is allowed tomorrow. Can I open this chat, or is lost today?
I'm not really sure about that. I have to check with the marketing team. I'm not really familiar with the WebEx
No, me
system.
neither. I'm scared. I believe that everything will be lost, at least for us. For you, no, but for us, but I will put it on my chat. So
Yeah. Actually, it's a very good
something
advice. Maybe I can do that as well myself.
eventually, Ali, you can ask the marketing people if they could save the chat somewhere, or just copy paste it in the mail that we received.
Yeah, I think if it's saved,
Maybe
we can
maybe
share
it's
it.
done.
Yeah. I have to check with them really.
Yeah. Okay. For the rest, thank you very much for organizing all of this, and thank you very much for participating, and for all you presenters. Ali,
Yep.
is it over?
Yeah, you're free to leave. If I'm just leaving it on for anyone of the attendees, if you want to ask any question or
Okay, then
share
I'll
something.
wait. Then I'll wait for you to say when it's over.
All right. Yes.
I
So-
really don't want to keep you if you have
No problem.
anything else, or also for other panelists, please feel free to leave anytime.
Okay, Ali, just a question. All a question. It's not a question. It's a requirement. All the questions that are being recorded, you need to place them in some file, an Excel sheet, etc., so that we can prepare something that we will then send back to all the attendees with question and answer, with the name of the name of the attendee that plays the question and the answer, and who answered the question. So that this is a typical way. So just keep track of all the questions, and eventually you can send this file to us so that we can answer the questions that have been placed by the attendees. Okay, and then
Sure.
we will reply.
We can do that, no problem.
Listen to them. Okay. All right.
All right. I feel that we might not have any additional questions.
Yeah.
Again, I would like to thank you all, panelists and attendees, for joining us in these 2 wonderful days. I hope you all have a good day, and best of luck.
Yeah. Okay.
Yes, NJ, please
To you.
end the session.
Hi Ali,
To you and
so I
everyone.
just shared the chat. I've just shared the chat and Q&A. I have saved it, and I will just share it with Ali to proceed accordingly. Okay.
Okay. Thank you, Ali. It was well organized. Thank you, Andrea. Thank you, Mauro. Thank you, all other participants, panelists, and the organizing committee. Sanjay. Thank you. Bye.
Bye-bye. Yep.
Thank you.
Okay.
Bye.
Thank you, everyone.
I will also leave now. Bye-bye.
Thank you to all of you.
So, Ali, should I close the
Bye.
session, Ali?
Yes, please go ahead.